class. How are you? Good. I can tell more of you came down further. There's still some of you that are resisting. I would still encourage you to sit closer and be chummier. But thank you. So, who wasn't here Monday? Oh, more than normal. Okay. Have you looked on the website yet and read some stuff? I got one reply. So the rest of you that are ignoring me? Not even looking up or acknowledging that you're... Okay, well, good luck then. I wanted to say is, if you go to Canvas, which is where most people start, there's a link to WebAssign. So you can continue with a free period and read the syllabus and see your homework assignments and the superhero paper and the schedule for the whole semester. So you've done that? You've started that process? Yeah, it's on there too. When you read the syllabus, it'll talk about that. Thus, then you'll be interested in reading it. We'll discuss the paper later. I haven't discussed it with anybody yet because until you guys read that, it doesn't make much sense. Before I get your question, I also wanted to comment that from the physics webpage, the home page, on the left there's a link to courses, and thus you'd see our course. That gives a link to WebAssign also, lest you don't want to go through Canvas. But I assume at this point soon you'll just have that WebAssign login link and bookmark it because you're using it all semester. Yes?
One of the questions in the assignment says how we are going to upload or bring a hard copy for the superhero.
Correct.
But doesn't say it anywhere. I've been reading the syllabus and...
It's in the superhero instructions.
It doesn't say how we are going to upload that or we are going to give you a hard copy?
No, it doesn't say the procedure. It just says that you are. Let me review the question so I can address it. Alrighty. So I'm logging into WebAssign right now. View that first assignment. Scroll down to there. How should your superhero paper be submitted? That's all the question asks. The options are electronically and in printed form, just electronically, just printed. That's explained in the superhero paper instructions. Yes, it is. I will double check that. You saw it also, someone else? It's not in the syllabus, it's in the superhero paper instructions.
It's another set of instructions.
Yes, it's on the web design. Yeah, it's at the very bottom box.
Yeah. In the syllabus, it refers to the superhero paper and says there'll be another thing to read on this because it's as long as the syllabus. So you go there. And the second page of that, for your benefit and mine when I'm grading it, since I'm there and we're on it, there's a rubric. So you can see this is important to me. This is what it entails, and that's how many points it's going to be worth. And this, and this, and this, and due dates, and how you turn it in. And I don't mind giving you an answer because the whole point of this assignment is so you know. Both. I'm going to require that you submit it to me electronically as well as in printed form. Electronically it's easy as an attachment to email. If you can't do that, then we'll work something out. You can bring it on a flash drive, you can send it to me some other way, you can scan it as an image, whatever. But
And the clicker, I bought the clicker and for some reason I cannot open it in my phone.
You bought a clicker and can't open it in your phone. Okay, that's a contradiction. You either have a clicker.
No, the clicker, no, the electronic version.
So you got ResponseWare.
Yes, the ResponseWare.
Okay, did you purchase an access code?
Yes.
Did it send you an email with your ID number?
Yes.
Okay. Did you download the free app to your mobile device?
I tried.
And it won't.
And I already paid.
That I don't know. You're the first one in 5 years that's happened to for me. What's your device? I mean, is it a? It's a phone. Is it old or fairly new or?
A Windows phone.
What's version? Do you know?
502.
Okay, yeah, that's not that old.
It's
So
Windows 7.
so you're through Google Play downloading the app? Has anybody else attempted that this semester? And through Google Play? What was the name of the app? Just called Responseware? Isn't that what you saw?
The thing addressed me to the App Store,
Mm-hmm.
and I look in every app. I went to bed almost 1 a.m. trying to figure it out, and I couldn't.
Wait, you couldn't find the app or you couldn't download it?
No, I couldn't find the app.
Oh, well, that's different. Okay, good. The app's there and it works. We'll get the app. It's called Responseware, just like in the syllabus. And that one word, response. And may I suggest that right after class that you two at least pull it. We can pull it up and see it. We're going to fix you up. Don't worry. Thanks for asking. Other questions about this course and the syllabus that might have come up since Monday? Great. We since posted Monday's lecture that was video recorded kindly by TLT at the university. The link is now there to get to it in YouTube as a playlist. So on WebAssign under announcements, you can see the URL, so you can copy and paste and bookmark that if you so desire. You know, to rewatch the fun syllabus talking lecture all over again. I'll give a quick shout out to Brett, my good friend. He saw it. I think he's the first one to watch it. He beat all of you. And I was like, really? You watched my lecture talking about my syllabus and you're not even in this class? Yep. But he was the first to respond. See, he had a chance. He texted me what he thought about this demo, which I left you hanging. So since I thought some of you might think I'm cheating, since I've had it for 2 days, since you saw it, I'll redo it. Let's just get my sponge wet so it'll work when I make a mess. So pour water in the middle. Some of you weren't here Monday. Any of you think about it?
Yes, I did.
All right, good. And you play the shell game, and you saw how terrible I am at it. But we'll try again, because what the hey? Okay. Raise your hand if you think it's this one. This one? This one? I've only ever fooled a few people. But obviously I fooled you. And as I did before, I turned those over. So, my question to you is in trying to make an analogy. Say like stars, astronomers, they can't go to the star and peek at it, right? So if I forbid you to come down and actually look inside, what's something else you could do to test, to see, maybe convince yourself or prove that one of these still has water in it? What do you think?
I have light.
Okay, what would we do with the light?
I can light the thing.
We'd shine it? Okay, what do you expect to happen?
I am going to see what is inside without touching.
How?
Light in the cup.
These are opaque, so the light won't shine through it.
It's plastic. Kind of. So if you do it for me, from here I can see which one is.
All right, should we try it? This is great. We'll see if it's bright enough. But you're right, if the light's bright enough. You thought it was this one, right?
No, put it up.
Like this? Here, we'll make it easier. How about... Yeah, I don't like any of those. This one. I like this. This is good. The rest of you are thinking of your ideas, right?
You see, it has double double glass or something in there. Yep.
Does look a little different, doesn't it?
Yep.
So very good. How about from behind? Can you see it at all?
Yeah, it's awesome.
Also, so great idea. Some people often come up with, what if you were to image it some other way? How do you image our body? Can't see inside it, can we? X-ray or ultrasound or MRI. And they all, since they're at different wavelengths, we're going to study a bit about waves, the size of the waves and the amount of energy they have. Yeah, will get absorbed differently by different things. So X-rays are great for seeing bones. MRIs are great for seeing soft tissue. So yeah, we just imaged it. There are other ways, though. Did anybody think of another way? Yes, in the back.
Are we allowed to lift them up to feel like a weight difference?
There you go. Weigh them. Now you couldn't do that with a star, but yeah, weigh it. That should answer the question if it's still there. Definitely. Good. And that was my friend's guess. He said, "Yeah, can we weigh them? You bet." What else?
Makes a different noise when you put the cup that still has something in it.
Sound differences when you're messing with the cup. There is a difference. So there's something special about this one, or at least different than those two. Very good. Nobody's said that one before in my years of this one. I'm going to keep asking. But the reason I do this is in the scientific process, again, you have to be able to test it. They call it science. And we come up with hypotheses. You're doing that now. What if we shine a light? What if we do this? Then I test it. This is easy, right? And we analyze the results. We can draw some conclusions from that. If it doesn't give us the answer or we're still not sure, we can revise or come up with a new question and do it again. And we just keep learning. Also, one of the main purposes of this course for me isn't to make you guys all physicists and understand all this wonderful physics, but hopefully you'll get in there how to think more like a scientist, which will help you in your life. You're going to be exposed to lots of different facts, experiments, news, media coverage, right? And they can warp things. How do you know whether to believe them? You know, for example, you could have a graph, and the thing looks like this. And so to emphasize, it doesn't change much. It goes up a little bit. What if you just changed the scale of this axis and you zoomed in and this took up the whole scale? What would it look like now? Whoa, it's on the rise. It's runaway. It's all in presentation, and you got to know how to interpret things. Think for yourself. You need to come up with ways so that you can test these things so that you aren't living your life ignorantly. Some people on purpose and some people not on purpose present things, and it can be confusing. So hopefully through this course, you'll learn to think for yourselves and be able to reason things out. So a few more ideas. Do you have one? Oh, it was you.
I got two hypotheses, I guess you could say. One of them is that you have a sponge attached to the bottom of it. So the way to test that would be to add more water at the beginning.
So we could, even without looking, put more water in it, right?
So more water than the sponge.
I like that. I like
The
that.
other one is just there's maybe a chemical mixture that turns into ice when you pour it in. And so that would just be a matter of waiting to see if it reacts different with time.
Chemical reaction in there and see if it reacts different with time. Some people go, "Why do you always repeat everything somebody says?" It's for the camera. So let's get to it. Yeah, it's not in these. You guys have been right both times. It's still in here. We've shown that twice. This is what it is. The cup just ripped. Some of you probably know what this is. It's sodium polyacrylate. Polyacrylate. More commonly known as baby diaper polymer. This is the powder that's inside baby diapers. No, I didn't grab this from a baby diaper. But I bought it, in bulk. But it starts out as a powder that I had in the cup before we ever started, and it absorbs hundreds of times its weight in water. So you can pour more in, and it congeals the water, traps it, and makes this spongy, messy thing. It's great. Turns into a semi-solid so that it doesn't fall out of the cup. So another thing you can learn is you can't always just trust your eyes, what you see, because that's not always what happens. And what you naturally think happens isn't always true either. A lot of times it is. I hope you guys rely on your intuition a lot this semester. I mean, I hope my questions and homework will make you go, I don't know. Well, reason it out. What makes sense? Make an educated guess based on what you know. At least if you're going to guess. Hopefully through my lectures and the book you can look up the answer. But think for yourself and reason it out, because most of the time you guys have the information and knowledge already. My goal is to teach you how to put those pieces together. Too often students will see a question, and instead of going, now that was funky, and no, I'm nowhere near the lights, so either someone's out in the back having fun, or they just went cattywampus. Anyway, there's one. We can think about why that did that. They are on motion sensors. Maybe I hadn't moved around enough. Anyway, where was I? Seriously, I did forget this time.
We have to use our common sense.
Thank you. Studying a question. A lot of times, unbeknownst to the student, they read a question and they start thinking, oh, okay, what do I need to know to answer this question? What did he teach us? Which formula is that? Which equation? Which chapter? Which topic? Instead of just, whoa. Instead of internalizing that and going, oh, okay, well, based on what Adam taught us, this makes sense. I probably need to apply this. And a lot of times they'll go through the question and miss it because you're trying to figure out how to answer the question. What do I need to know to answer this question, instead of actually using your common sense that you've gained, that you will gain, that a lot of you already have. So I'm going to draw lots of analogies in this class, because for me, it's half because I'm lazy, but it's more because I don't learn it well otherwise. I don't retain it. When I learn a new piece of information, if it was always new, I think I would lose track. I couldn't keep it all filed away, you know what I mean? But if I can relate it to something I already know, I can tie it to something that's already solid and I've built my neuron pathways around, I'm going to remember it better. It'll make more sense to me, and I'll be able to apply it when I need it, instead of, what was that? I don't know. Where did I put that? So if the more analogies and basing on your past experience you can do, the better. All right. Any questions about this? Says you get a trash can. All right, I'll leave it there in case some of you want to feel it afterwards. Some people like to do that. It's safe. Okay. So, see, we've already went over most of Chapter 1. Scientific method, hypothesis. There's a few other terms I'd like to emphasize that it does also, because people in the non-scientists get them confused sometimes. And so that we're all on the same wavelength. A fact. In normal world, I would say most people think of fact as something absolute. It never changes. In your book, it says it's a close agreement by competent observers. That's my favorite part. Competent. A close agreement by competent observers of a series of observations of the same phenomena. This definition is in your book. It's defined in there, lest you don't feel the need to write it down. But a fact. Pretty much people agree on it. We observe something, we make lots of observations. It seems to be that way, and we go with it. Like the world is flat. That was a fact. But that's the one I like to use because everybody's heard of that one. But it changed, didn't it? When we got new information and most people agreed, no, that's not right. That went away and we had a new fact. The world is round. So facts can change. Doesn't mean you can't trust them, because that's what we know at this point. It's a fact that if I drop this, it's going to fall. And I can tell you how fast it's going to fall and how long it'll take, because we've observed this. When you put lots of that stuff together, you can create a law or a principle, which is in your book. It defines it as this: general hypothesis or statement about the relationship of natural quantities that have been tested over and over again and has not been contradicted. So we make all these hypotheses and statements about these relationships, what you thought was going on here, but you've tested it over and over and over, and it always works. We've never seen a contradiction, such as, it always takes this long. It's always under these conditions, blah, blah. It's always that. So we call it a law. There's a law of gravity. There's laws of motion. That's our next several chapters that we're going to study before our first exam, are laws of motion. And then the last one is a scientific theory. A scientific theory. So let me write those two. And that's even bigger, as defined by your book. A synthesis of a large body of information that encompasses well-tested and verified hypotheses about aspects of the natural world. So a theory is this kind of like this model built up involving laws and facts. You can have an individual fact, these relationships that seem a bunch of facts lead to, you create a law of motion. But you could have a theory it's even bigger. It encompasses more of these, several of them, that help us understand the world around us. Probably the most common theory you guys have heard of is the theory of, I've seen what pops out, of what? Theory of evolution. Theory of relativity. Yeah, those are the two most common. See, they're always the first two that pop up. They're built around a bunch of laws that have been well tested and individual facts that have never been contradicted. But all of these can change. In the real world, normal world, non-science world, a theory, they hear that. Oh, that's just a theory. That's what you think. But nobody really knows. And that's probably the biggest conflict between non-scientists and scientists. It's just a theory. True. That is absolutely true. But it's the best thing we have. And it's based on a whole bunch of well-verified, tested natural relationships that we've noticed that nobody's contradicted. And it's served us well up until this point. The theory of relativity there, that's how you can use your phone. GPS relies on the theory of relativity. If it did not account for it and use it, your phones would be, location-wise, GPS and all that, the Army and Navy, would be useless. So we rely on it. It works. If we learn more new facts, find something that contradicts, we'll adjust the theory and we'll go with that. So that's what physics is. I'm going to introduce you to lots of laws and facts and equations, and those are going to be our guides to thinking, how we should understand relationships between things, because it works. And if you guys think of a way to contradict something, you'll be famous. Any questions about that? I want to emphasize again that in science it's got to be able to be proven wrong. You've got to be able to test it. If you can't, because it's ambiguous or you'll never know, it's not really science. Scientists like to test things. If we can't, we're sad. we call it something else. And so a lot of scientists that can't admit that they're wrong, you've probably heard of things where they present a paper and it comes to be wrong because nobody else can reproduce it or whatever. A respectable scientist would admit that, readjust, and move forward. Those that deny it aren't playing the science game very well, and they don't last very long. Well then, you ready for chapter 2? So chapter 1 was about science. Again, I want to emphasize the schedule. on WebAssign says what I'm lecturing about each time, so you know what I am going to be covering, and when you forget what was covered, when it comes exam, oh yeah, all those are going to be on the exam. So you can all refer to that, go back there. Chapter 2 is, oh, that's my word, what does he call it? Just that. Newton's first law. Inertia. That's the key term in this chapter. You guys have heard of Sir Isaac Newton, right? I hope. At least heard the name. Give me something. Okay, good. Most of you I'm seeing nod. He's famous for many things. You're going to get to know him well for laws of motion. He had 3 laws. And, you know, when this class is over, it's not mission critical that you know which one was which. But as long as you know what they are. In other words, was that the first law or the second law? That's all right, because I will more often refer to Newton's first law as the law of inertia. Because that helps me remember what it was. And I would bet lots of money that 90% of you already know what this law was before you came into this course. You just didn't realize it. Here goes. Okay, wait, okay, who's read chapter 2? 1. Okay, well, that's okay. Shame on you. That's all right. It's the beginning of the semester. But that will prove my point more. That means you haven't already read the answer. Newton's first law of motion is things at rest stay at rest, and things in motion. See? Who's heard that before? Is that 90% of you? Good, pay up. That's the law. That's what it is. It's because of this thing called inertia. Your book defines inertia as sluggishness. I like that word. Sluggishness. Or apparent resistance of an object to change its state of motion. That's how I usually define it. A resistance to change its state of motion. Now, state of motion is how it's moving, its velocity, how fast it's moving. We're going to learn that more later. So it's a resistance to changing its motion. So when I probably slip and start saying it's a resistance to change, it's a resistance to change in general, remember what it's trying to change. It's a resistance to change its motion. Good. Get that in your head. So something that's moving wants to keep moving. It'll resist changing its velocity because of this property called inertia. And this cup, that's a state of motion. Its velocity is what? 0. Some of you are going, it's not moving. That's a trick question. 0. So it wants to stay like that. Things at rest want to stay at rest. And so it will resist you trying to change its state of motion. I did it. But I felt some resistance. This isn't light, you know. That's all inertia is. It's a property of matter that helps us define it's an object's resistance to when it's changed its motion. That's the key to this whole chapter and a whole lot of physics. Now, I hope to repeat this again. Inertia is not the reason a moving object continues in motion. Inertia is not a force. How would you define a force? We do it all the time in physics, but you know, lay people, they're like, force? You know what it is, but have you ever tried to define it? Now's your chance. How would you define force? Speaking to your mom. You're in this physics class. What's a force, honey? And you tell her what? Give it a shot. If you haven't noticed already, I'm one of those teachers that doesn't answer his own questions. I'm patient. I can wait. Anything. We'll add to it. Oh, bless you. Pressure. That's good. Pressure involves a force. We're going to study that later too when we get to fluids. Technically, pressure, so you know, is acting over an area. So it depends on how much you're pushing on. But it's a force over an area. That's pressure.
The cause to an effect?
The cause to an effect. Yes, forces are generally causes that have an effect. In this case, am I exerting a force on this? What effect is it having? Movement. It's changing its motion. Its velocity now is not zero. So yeah, there's a change. Good.
Isn't it like mass times velocity?
Mass times velocity. You're remembering things. Since you brought it up, I'll go ahead and write it. You were very close. Force is mass times acceleration. And I have no qualms about doing things in different orders in this class as they come up. This is essentially Newton's second law. So when we get to it and I go, here's the key, that's the key. I prefer it like this. We'll cover that more. This is a symbol that means proportional to. Proportional to. Because, again, equations are guides to thinking. They're just shorthand notation to help us remember relationships. That's how I intend to use them in this semester. So those of you that, raise your hand if you hate math. Raise your hand if it scares you. You're worried about being able to solve these problems in this semester. Well, a lot less of you than usually raises their hand, or you guys aren't participating. See, if you don't help me know, I can say, oh, you're not scared. Good, I'll just whip them out. You got to be honest with me. But that's what it means. Acceleration, and we're going to learn that more too. But you already know this. You step on the accelerator in your car, right? And what happens? You go faster. And in physics terms, that means you're changing what? Your distance over your time. Or somebody might think you're changing you could call it something else. Velocity. Those are the same thing. Or you're changing your state of motion. You're changing your velocity. That is distance over time. Very good. We'll get to that too. Yes?
What's the difference between velocity and acceleration?
Good. So an acceleration is a change in velocity. Here's a Greek term that I like to use. It's shorthand. It's delta, but it means change in velocity. It's one way to think of acceleration. It's a change in velocity. So when you're trying to change something's state of motion by going from zero to nothing, or something to something faster, or even slowing it down, all of those are changing the velocity. Thus, it's accelerating. And we just learned from Newton's first law that in order to change something's velocity, what has to happen? It could be moving, but it could stay at the same speed, not changing its velocity. 55 miles down the highway. Wait, this is Utah. 85 miles down the highway, but constant. We're not changing the velocity. But let's say now you speed up to 95. There was a change in velocity. Try to put these pieces together and reason. What's the only way that change of velocity could have occurred? I like both of those. Very good. You've overcome resistance. What is resistance? The resistance to change its motion. Inertia. Your car has inertia. And in order to overcome that, you have to apply a force. So it's the cause. The effect is you change your velocity. Force is like a push or pull. It's something that causes. Did I write it down? Any influence, a force, any influence that tends to change the motion or accelerate. Same thing. An object. Any influence that tends to change the motion of an object. So, back to Newton's second law, the acceleration is proportional to two things. The force and how big the object is. This is mass. Well, I said that, but... And it's all because of Newton's first law. If you push on something, it'll change its motion and make it go faster. Or if you push it in the opposite direction, it'll make it slow down. It'll change its motion. And the bigger that force is, the greater the change. That make sense? But look at here. The bigger it is, the more mass it has. How do you think the inertia relates to mass? More resistance. So the bigger something is, the more it's going to resist you. That's why it's in the denominator. If this value gets bigger mathematically, what happens to A? That's why, yeah. So we say the mass and the acceleration are inversely proportional to each other. Inversely. When one goes up, the other goes down. Whereas force and acceleration are directly proportional. You increase this one, you get an increase in that one. And I've already exposed you now to Newton's second law. I'll revisit it when we actually get there, but yeah, it'll go quicker now. So that's Newton's first law and second law. Demos. Let's show this to you. All right, who's ever tried to pull a tablecloth out from underneath the silverware? Raise your hands. Nice and high so I can see. See, look how many people have tried that. Okay, if those of you with your hands up, keep them up if you were successful. Only one hand? So all the rest of you broke the plate? Is that what? All right. Who has never tried it but has always wanted to, but you were afraid to because you thought you'd break something? Raise your hand. A few more of you. Well, today's your lucky day. Who would like to try it? All right, come on down. I'll give you 3 tips, and we'll give the whole class so you can all go home and try it. Tip number 1. The key to this is these have mass, so they have inertia. So they have a resistance to wanting to change their motion. They're at rest right now, correct? So they want to stay that way. So basically, if we can pull this tablecloth quickly enough out from underneath it, they'll stay put. There wasn't a big enough force to make them change their motion. You do it slowly, they'll start dragging. So we got to be quick. So the first tip I have for everybody is don't start right here. Because as soon as you start pulling, they start moving. And you're not up to a high speed yet. So I might suggest have a little slack like this. Start like that. So by the time you get here and it starts pulling on these, you're already going faster. Does that make sense? Tip number 2. Go down, not up. It's a practical tip. Down. A lot of people get worried. I got to go fast, and so they ramp up and they go. Well, that'll apply an upward force, and it will respond accordingly. So yeah, don't rev up first. Just go down. And tip number 3, you can get comfortable. Cut the seam off. It's really annoying. It's funny, but it's true. Cut the seam off. Otherwise, when it goes underneath, it'll bump it up.
Can you do it first?
Nope. And you know what? I'm going to make it even harder for you.
Oh.
Okay, go ahead and get comfortable. Go ahead and grab, get a good hold. Don't pull yet. That'll be good. You get a few practice motions. You're going to go down. Start up here. All right, we're going to give you a drum roll.
Oh, shoot.
And when you're ready. Hey! Very good. You did it. No.
Broke one.
Nothing's broken. I can go back to DI and get more plates. That's where I got this one. All right. Very good, and thanks for helping. I'll ask for lots of volunteers this class. I hope you guys will spread the wealth out and help me out and volunteer. But you guys are good scientists. You made observations. I know you did. Tell me some observations. What happened? What did you notice? Anything?
I closed my eyes.
You also started going up, and I got a little worried, but it worked. Yes?
The silverware has less mass, so the force kind of...
Very good. Yeah, this one like, whoo. And tell us why again? These have less mass, which means they have less inertia. And inertia is a resistance to changing their motion. Since they have less inertia, they have less resistance. It was easier to move these. since we've already laid it on you, for the same force applied to everything, these have less mass. So they were accelerated, changing their motion more. Yeah, and they flew off. What else do you notice? I thought I'd at least ask you. Yeah.
When you put it liquid in the glass, so it also had more of a mass, greater resistance, so it was actually really easier for her.
Excellent. Yeah, I like to scare people by pouring the water in, but it actually helps you. It adds more mass. So, yeah, these two hardly moved at all because they have more inertia, more resistance to change their motion. So, yeah, see, I was helping you out. Let's do another one. This table, I have some. We won't finish all of them today. We'll finish Friday. Let's do this one. Come over here. I need another volunteer. Who already doesn't kind of like me and would like to hit me? Well, good, because it seems like every semester somebody raises their hand, even if it's facetiously. So thank you. But I do need somebody to come hit me. Okay, thanks. She had a big smile on her face. Okay, what we're going to do is, this is a lead brick. It weighs 26 pounds. And what we're going to do is I'm going to have her get over here. And I'm going to put my hand underneath it and ask her to hit me. Hit the brick. So, yeah, I'd appreciate it if you don't miss. Start soft. Get the feel. Now whack it as hard as you want, as long as you don't miss. Ah! No, I'm just kidding. Go ahead. Harder.
Still?
Harder. Yeah, I don't feel anything. You want to try it?
No.
Here, do it yourself. Put your hand. I won't hit you. Put your hand under there. Now this is 26 pounds, so this is kind of heavy. So adjust it so it's comfortable. Here. Okay, go ahead. Start slow. Work up to it. Yeah, nothing, right?
No.
Harder! There you go. Give her a hand. Thanks. All right, we've done an experiment. We need to analyze the results. What do you got?
Because that is so heavy, absorb the whole pressure.
Yes, see, that's good. It's because it's so heavy, it absorbs the pressure. You guys are going to do this, and I hope you do, even though you don't know what the words are. See, I could tell, yes, what you're thinking is correct. What came out your mouth wasn't. That's okay, but I could tell it's not pressure, it's force. And it is absorbing the force, but more technically it's absorbing the energy. We haven't got the energy yet. So in terms of what we know, Newton's first law, it's heavy. So that means it's going to take a lot of force to change its motion because of its inertia, its resistance to change. So yeah, the hammer is trying to push on my hand and the brick. Push on the brick, which pushes on my hand. But this has so much inertia, it resists changing and moving much. So I don't feel hardly anything. It's just fine. Yeah. It only hurts because it weighs 26 pounds. Yeah?
But if you were to use a bigger hammer, would that change? 'Cause then it has
Should I go get one? I got a sledgehammer.
Yeah.
No, you're right. Which variable? If I use a bigger hammer, it gets more dangerous, yes. Why, though? I heard it. More force. If you apply more force, it's going to cause a greater change. And at some point, you apply enough, I'm not going to have a hand. Yes, that's correct. Good. While I'm using the hammer, I like that example. I use this one specifically. It's wood with the head on there. Often the heads get loose. Raise your hand if you're familiar with that phenomenon. Well, good, because it's getting less and less with the new generation of modern hammers with fiberglass and solid units. Do you remember things you could do to tighten the head? Put a wedge in it, which they've done, some screws, and splits it out. What else could you do? Glue, yep. What's that? Hit it on the counter, and that's the one that applies to here. You could also soak it in water because it'll expand and get it really, really tight. But yeah, that's what you do this. Now it's tight. Why? I applied a force, yes. That's not enough to explain the phenomena. While you're thinking, because you're thinking, right? You're going to learn more in this class if you think. So here's my hammer. This is the head that's free to move. It's loose. When I go down, look what happens to the red block. See where it's at now? And I saw some light bulbs. So what's happening? What's this stopping force? Which object is it applied to? To the wood part? Start back up here. Is it only applied to the wood part? Is it only applied to the PVC pipe?
No.
Right? Both of these are moving, right? Now their state of motion is moving, as they have some velocity. Which one am I directly stopping? Either the handle or the PVC, right? Well, the head and the red block have inertia. Things at rest want to stay at rest, and things in motion want to stay in motion. So does this. Unless a force acts upon it to slow it down. So the friction will eventually slow it down. But after you stop the handle, it keeps moving a little bit. And that'll make the head more snug, tighter onto the handle, onto the wedge. Now, last thing. I'll stop here. Okay, you got this down, right? Make sense? All right, thought question then. What if, instead of hitting this onto here, I take this and hit it on here? Will it go down further? Will it stay put? Will it go up? See, this is where I could do a clicker question. But you guys are working on that, right? I could ask you. So raise your hand. Who thinks it'll stay put? Who thinks it'll go down further? Who thinks it'll go up? Some guy in the back. Who didn't vote? Who doesn't care? Good, nobody raised their hand. All right, think it through. This is exerting a force on these two objects, trying to change their motion from rest to moving, right? I'm going to hit it down. They're both going to be moving down. It went up. And you know what? I feel like you guys should think about that. We'll discuss. This is where we'll start next time.